Okay, live stream's running. Everyone's logged into Slido. I think we're good to go then. That's a bit too small. Okay. We left off last time discussing some bags. So all sorts of data structures that can be described as they have an operation to throw a new thing in, and they have some operation to take elements out. And we've seen three different types of bags. The general bag, where we don't say anything. It could be any order that we get the elements back out. So when you delete any, the implementation decides what you get. And we've seen stacks and queues where the order was prescribed to follow the insertion order one way or the other. Stack, you always get back what you put in last, like a stack of things where you put something on top. That's the first thing you have to get off. And a queue, whatever you stuck in first bubbles through the queue the fastest. And so what you get out of the queue is always the oldest item currently in the queue. Today we'll look at some more sophisticated types of bags. In this next section on fundamental data structures, we'll look at priority queues. That's the abstract data type, and the implementation that's most well known and say most befitted for the fundamental data structures topic, at least, binary heaps. Before we start, let's see. This is basically just checking what you've had about this before. Once I get there. So you're not really supposed to know this already from what I told you, but you might know this from undergraduate classes. So without much further comment, I'll leave that question open. And we had, well, 47 people made it for the attendance code yet, but there's a few people coming late. I'll show the attendance code later again. So I think we should aim for at least 50 answers on that one. I should give you a fair chance to read the question and put in your answers, but it's independent of the next slide. So most people seem to be looking at me or the slides or both. So let's introduce the key abstract data type of this section, and that's called a priority queue. I put this funny, this is supposed to be first class in your airline. So one of the perks of flying first class, not that I've ever done it, but I heard it exists, is that you get priority boarding. So there's a queue when you line up for boarding the plane. And if you're ordinary people like us with a cheap ticket, you have to line up in a queue, as we've seen it last week. But if you bought in a higher priority, then you can skip the queue and go in first, independent of the insertion order in the back of people at the terminal or at the gate. So a priority queue is kind of capturing this, and I hope that this picture sticks in mind better than anything I could draw. The formal operations are like this. We'll also have the operation to start with an empty priority queue, but we'll generalize this a little bit. Here's an operation that takes a given array or list of items and constructs a priority queue from that. We'll focus on when it's given as an array, because that's most convenient for binary heaps, at least. The most important operations are insert and delete max. So insert inserts a new element into this priority queue, into this bag. And we're giving two different pieces of information: the element itself, x, and some number or or at least some element from an ordered universe, a priority p. And so when you ask for an element in the queue, all you can do is really get the one with the highest priority. That's why this function is called delete max. It gives you back whatever element currently is in the queue that has the largest p. All right? There's a few other things. You can peek at what is currently the one with the largest priority. And there's a way to change priorities of the things that are currently inside the priority queue. Sometimes we can also support a delete operation. I left that out here because it doesn't add much to our story. And you can check if it's empty. Priority queues are a convenient building block. Whenever you have to deal with things that arrive out of order, but you want them in some sorted order, but it's a dynamic process. You can't just wait for all the elements to arrive and sort them. You want to be able to insert them and get some out intermixed. Apologies. So we meanwhile got a lot of people voting. I don't really want to show you the results right now. We'll come, or you will discover what the right answer is later anyways. Let me instead switch back to the attendance code before we need another question. The way I formulated the priority queue ADT here is the way that our key source, this textbook, the red textbook, Algorithms by Sedgwick and Wayne, formulates the problem where you can delete the maximum element. You can also have a symmetric version where everything's flipped. So instead of the maximum, you get the minimum. The rest is all the same. Now, a priority queue can always just do one thing. It can either get you always the maximum, or it always gets you the minimum. We don't, at this point, consider that you can mix these two operations. So I just listed this here in detail because many other textbooks prefer the min-oriented version. But if you have an implementation of one, you could think of just negating the priorities, and then you get the other. There's usually simple tricks to go from one to the other. So let's see if the definition of the priority queue is clear to everyone. It's not a trick question. It's not anything really spectacular. We got all the way up to 67. No Wi-Fi. Oh, cool. You might be able to get by with mobile, because at least this room is at the edge of the building. I mean, I told you why I'm not live streaming over Etiarome. Okay, I'll if it doesn't come back, maybe we'll just take this question out of the participation. I'll have seen that you logged in earlier. Did you have the issue before for the previous question where it just died out now? All right, let's pretend you all answered 9 in this case. Or most of you did. So the thing is, it doesn't matter for a priority queue in what order you insert the elements. The only thing that matters is the value. If I write it like here, that we just say insert these numbers, then the meaning is that the item X and the priority P is just the same thing. That's often a simplification, if you want, for the syntax. If the element itself is ordered as a number, you can say the element and its priority are the same thing. That's what was meant in this case. Okay, so we defined an abstract data type. That is our wish list, what we would like to be able to do. Now, we should also think about how to realize that. And before we start with something more sophisticated, let's think about how far can we go with just the very simplest ideas. And I think it's usually, it doesn't take more than a few minutes to come up with these two ideas. You can either have the elements in some random order, maybe you keep them just in insertion order. Then insert is really cheap. You could, for example, use a resizable array from last week, or a linked list would also do. But if you want to find the maximum, there's nothing to help you really to speed up that process. So you have to go through all the elements and find the maximum. To be clear, linear time for the operations here is not interesting. You could just do that without any data structuring. A sorted list seems more promising. Where after all, we're trying to get the maximum, right? Which is, we can at least find the maximum very easily in constant time. If it's say a doubly linked list, we could also remove it in constant time. But now insertion has become more tricky because, at least if it's a linked list, it's not clear how to put the element at its proper position without walking through the list. So both of these are not really satisfactory, but they're easy to program. That's one thing. So we'd like to get something in between. This had very fast insert, this had very fast delete max, but the two other operations were really slow. Can we get something that's in between? In a way, what we want is a slightly sorted list. It should be sorted enough to get the maximum fast, but not so sorted that it takes ages to insert. That sounds a bit weird, right? But that's exactly what a binary heap is. If you look at it from the right way, it's really a slightly sorted list or slightly sorted array. The confusion often arises that people talk about binary heaps and mean two different things. They are equivalent in a way that I'll talk about in a second. But you usually see one of these two descriptions first. And if you've seen one but not the other, and someone talks about the other and not the one, you're confused. So I'll try to start by showing both. Pardon?
I think we're going to change the style of asking to hold on. I think we're going to change the style of asking to hold on.
What do you mean?
I said I thought you needed to change the slide of asking to hold on. That was
OK, let's maybe take that offline. So if you look at the heap, you have an array, and you require, instead of sorted, where you would say every element is smaller, is bigger, say it's the other way around, we want the maximum. Completely sorted would be, at every position, the element is bigger than the one right to it. Now here we say something weaker. We say every element further behind is smaller than half of its position, right? Sounds like a completely weird and useless definition, but that's one way to define a heap in the array notation. And the other is a heap-ordered binary tree, and we'll come to that in a second. I think that's the point where we want to talk about binary trees, right? That hasn't occurred yet. So there's a few things that pop up in this that some of you may know and others may not. The first is the notion of a binary tree. A binary tree is any kind of ordered tree in mathematical syntax where we have nodes, and they can have two children. They have a left and a right child, and both can be empty, a null pointer if you want. I think it's most natural to imagine that these are objects, and they have two fields, which are pointers. They have a left and a right pointer. And so every element can have another 2 children, or it may not have one. And it could also have just a single child, as in this case. And then the left pointer would just be null. Now, people often don't draw the null pointers, just to be a bit more concise in the drawing. So that's a binary tree. Definition is every node has 2 potential children, a left and a right one. Both could be null or some other binary tree node. And we don't allow loops. So if someone is pointing downwards, you have to follow. There's no way that this guy's child is one of the ancestors. That's not allowed. No weird family constructions. Now, a complete binary tree is one where all the nodes have 2 children, except, well, we have to stop at some point, except maybe on this last level. There it's fine if some nodes have no children, but if so, they should be all flush left. So we want this, this kind of shape here. We want up to the penultimate level, every node has exactly 2 children. And then on this last level here, up to some point, they all need to have 2 children. Then there could be one node where potentially has just a left child or none, and then the rest have no children. Okay? That's what we mean by a complete binary tree. And now this last bit is about labels on the nodes. As the annotation says, if you have labels assigned to each of these nodes in the binary tree, so each of these circles additionally has not just left and right pointers, but also a value element, then every parent should have a label that's larger than the labels of all its children. And if you think about, if this is true, then the root must be the largest element in the entire thing, just by induction, right? The root is bigger than its children, and these are bigger than their children, and so on and so forth. Okay. Now we have these two things that both seem to have some notion of slightly ordered, but what really brings them together is this notion of level order. So let me draw another little complete binary tree. And level order means we go through this tree level by level, and we assign indices to the nodes as we visit them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. If you do that and you write the labels of these nodes, so the green ones are indices in this level order traversal. The nodes would also have some values associated with them. So you could write down an array where you have the indices here and then the values. The first element would be the label of the root, which, as we figured out, must be the biggest, the maximum of the array. I don't know. I can peek at my example. So this will be, probably doesn't match with the numbers. Oh, by accident it does. Okay. So I'm just putting in some numbers here. That could be, they're arbitrary in a way. Okay. And they'll match the example on the next slide. I just wanted to put them here as well so that you can check. For any position, if I go to, say, position 7, if I half 7 and round down, that's 3. So I should check 70 is bigger than 10. That sounds right. And that should be true for all the positions. And that's not really magic. If you see where 7 and 3 are in this tree, then 3 is here, 7 is here. So, 7 is a child of 3. And you can work out that this is exactly what happens. Taking an index and halving it round down is going to the parent. All right? So the two things are the same. You can either write it as an array with satisfying this weird condition, or you can have a complete binary tree with heap order on the labels. The same thing. All right. Here's a bigger example where I put, instead of the circles, I just put the labels in. That's the same tree as we had on the slide before. And so whenever you walk from the root downwards to some leaf, you follow a path that is strictly that's decreasing. Doesn't need to be strict. Haven't said that. So in a way, it's slightly sorted in this sense, right? There's many paths you can follow which are sorted. And if you think back how they look in the array, they go basically from left to right, but they skip many elements in between. So that's a lovely definition, but why would you want to work with such a weird structure, right? That might be something on your mind. Now, in anticipation of what comes, let me copy this already. I want to motivate before we see why it's useful, why maybe this is a good idea, why it's convenient. Question?
So it seems to me like you can use the same array distribution of binary heap to implement arbitrary binary trees, where the children of each node is, the children of the ith node is 2i and 2i plus 1. So you could implement all like binary trees as an array.
Yeah, so the question is, can you generalize this kind of mapping from tree to an array to arbitrary trees? In a way, yes and no. You can always do it, but you might waste a lot of space. Or you need to think of some other way. So suppose the root has just a single child. And say that's a right child, not a left child. You want to kind of retain that information. And so that means, if the root has just a single child, also the next level has just one node. And so you're having a gap in this level order. And you need a mechanism to either memorize where the gaps are, or you need to leave space for the largest complete tree that contains the one that you are representing. And that might be exponentially bigger. But yeah, it's a useful concept to linearize data structures like this, because working with arrays is usually much faster. Jumping to a specific index is usually faster than following pointers. In our case, the shape of this tree is quite convenient, and I want to motivate why. So why do we have complete binary trees here? First of all, it's simple, because there's really, for every size, for every number of nodes, there's a single shape the tree can take. There's a single complete binary tree with n nodes, because everything's prescribed. It has to be completely filled at up to the penultimate level, and then everything else is flush left. So there's really no leeway. Another good thing about these is we'll see that we'll have to work down paths from the root to the leaves. And if you've seen heaps before, you know that. So having trees with small height is good. And the complete binary trees are the binary trees with minimal height for a given set of nodes. Intuitively, just because we stuck all the nodes as high up as possible until there's no space left. So how would you possibly improve upon that? Whereas in general, a binary tree could be a long chain of just left links. So that could have linear height, whereas this one has logarithmic height, as we'll see. And then lastly, the facts. That's why the question was really helpful here. The fact that we have this completeness, that we fill up all the levels up to where possible, means that we have these very simple formulas to go from a node to its children or to its parent. Okay? The second bit of the definition was heap order. And that one's more obvious, I think. At least one thing is obvious. If the maximum's at the root, that's good if we want to find the maximum. Then we can just look at the root and we know it. Now, deleting the maximum, the other key operation in priority queues, will have to work a bit harder, but it's doable. The other thing is, it is sorted, but only very mildly so in a way. There's many leaves which are completely unordered. If you think about it, nothing tells you if two siblings are ordered this way or that way. There's no restriction. So there's still many assignments of the labels to a heap left that are valid. And we'll exploit that for fast insert.
Yeah.
Question?
Yeah. Yeah. Sorry. Yeah. So the insert should be logarithmic, right? Since the height of the tree goes logarithmic with the number of elements.
The height's logarithmic. I haven't told you how the insert works yet in a way, but you will be right in a way. Yeah.
You find the nearest accessible leaf, and since height is logarithmic with number of elements, then insertion should be logarithmic with number of elements in the
yeah, that's true. Eventually, the operations are all dominated by the height in one way or another, and that means they're logarithmic at the end of the day. We have this question that I didn't really discuss, so by now you should have seen the right answer. Just to recap that. So the remark is exactly the segue to the next section. I've told you what a heap looks like. Now we want to do something useful with it. And data structures are only really interesting if we can change them dynamically. So in this next subsection, we'll look at the operations on binary heaps that allow them to implement all the priority queue operations. And I'll only very briefly explain the code and then show an example. And for more details, I'll refer you to the extra material on the website. So in particular, I don't want to show detailed code. I think it's, for most of you, it's repetition. For the others, it's probably too quick either way in the time that I have. But the videos explain this lovely in much more detail. So how do we insert a new element? If we take our heap from before, if you look at this heap and you want to insert a new element, by the severe restrictions on the shapes that we allow, there's only really one spot you can go with a new element, namely on the last level, the next element here on this flush left. So I don't know, I inserted 68. Now, okay, my drawing is not so nice, but this is, of course, the left child of 40. Okay, that's brilliant. So the shape is satisfied. We have a new complete binary tree, just one bigger. But we messed up the heap order because now this one's smaller than this one. So we can't leave it like that. And to conserve this, so this is the other way around. And that's bad. Well, let's say it's not like this. So what can we do? Well, if two things are out of order, we can just swap them. Exactly. I think this is too big. I'll try to keep the intermediate stages on the slide. So the first step would be swap the 68 up here, and 40 goes down. That certainly fixes this one. Let me get rid of this blue part here because that's just confusing. Now this is fixed. Now observe that the other child cannot be messed up by this. We still have that the parent is bigger than this child because it already was smaller than the 40, and we replaced 40 by something even bigger. So it cannot possibly violate the condition after that. Okay? And that's important because otherwise we would potentially have an endless number of violations that we create, and so we don't really fix anything. But that's not the case. The other sibling is not a problem in this case. Now we still aren't done because this is not true. So we do another swap. I might just fit or just not fit. You'll have to remember the order. Aw. Ah, cool. I think I created a problem. This one's too far out of the slide that I can't mark it that way, but I can grab it with the other tool. All right. It's not the point to get perfectionist. I also copied the wrong one. Brilliant. So more effort to fix it. So let's see. We had the 40 already down here. We had now swapped 66 to here, and 68 ends up there. And if you check now, all the conditions are fine. This is true. This is still true. And this is true. And now this is also true. Now, see, there's another thing we should think about. When we swap those two, now we did actually put something smaller here, right? That's potentially danger territory. It's still, in this case, fine. Because if you look at what there was at the very beginning, we know that the 66 is still bigger than the 40. So it was fine to put the 66 eventually up down here. And it can't violate any of these links. Because they were fine before. We replaced them with something that's only bigger, so they're fine after. So you see how this is very naturally framed in terms of these precondition postconditions that we talked about for verification. In many cases, data structures have something like an invariant as well. It's not a loop invariant necessarily. It's more something, maybe you can call it a structural invariant. So in our case, we say a binary heap, if you don't disturb it at the moment, must be a complete binary tree, and it must be heap ordered. And now every algorithm that we work with can use this as a precondition. It can rely on this invariant to be in place, and then you can prove correctness based on that. That's exactly what we did. Why are these green inequalities true? Well, because the invariant guarantees them indirectly. Okay, so that's insert. Is this the same problem? No, here it works. I want to comment on this name swim. So people sometimes call this process letting that element swim up the heap, because you basically imagine this was some bubble of air in water, then it would just bubble up the heap. Swim up until to the point where it is denser than the parent, but not less dense. Well, until it has the points in the sorted order of densities. That's how liquids sort, right? All right. That's insert. How do we deal with deleting the maximum? So we've already said it's really easy to find the maximum. Okay, that's the one with the broken 68, but let's just get rid of this again. It's never been there. You haven't seen it. Right. it's easy to find the maximum. It's the 87, no deal. It's in the root. So we can just take it out. And we want to store this in a temporary variable and return it at the end, right? That's all right. But we've created a hole in our fine heap. And holes are not allowed, right? This is, we can't accumulate holes, not part of the invariant. So again, we have to reestablish our invariant. And there's two things that are broken. The shape is broken and potentially the heap order, well, depending on how that interacts with holes. The first thing is the shape. Let's fix that again because that's easy. The only way to make the heap one smaller is by removing this slot, right? It's the only way to go. Now, we have this element 25 there, and we have a hole up there. Sounds natural to just do the obvious thing. So let's stick, no, that was not the one. Oh, it insists. Oh, come on. What is this? It's always a new bug. Let's try a different tool. That seems to work. Don't ask me why. It's the beauty of open source software sometimes. So let's take the 25 and just stick it in the root. But I guess you can already see that this is not really the solution. At least not the final solution. So the problem now is we repaired the shape, but we again violate the heap order. As you can see here, so this is no longer true, no longer true. So we even messed it up with both children. So what do we do now? We'll have to somehow repair this by swaps again. But we have two children that we could potentially swap this new root with. And we have to be a bit careful because we have to do the right one. So what we do next is we compare the two children. And remember, the invariant doesn't tell us anything. They could be in either order. The bigger could be left or right. We don't require anything. In this case, this one is the bigger one. We want the bigger ones high up. So natural operation is to swap these two. Okay. So let's do that and see how far that gets us. So we fixed this one, we fixed this one. Oh, one too much. We fixed this one, we fixed this one. But we potentially created trouble because we replaced the big element by a small one. And this time, the invariant is not going to save us yet. And indeed, we have a violation here, right? So we have to keep going, do another swap. Again, we compare the two children. 25 is the bigger among the two children, so we swap it with that one. Okay, that's not going to work again. Now, in this time, we're fine just because we ran out of children that we could potentially mess up. And that's the usual way how this ends. We just trickle down the heap until we've reached the leaf level, and then there's no more children that could be out of order. Oh, come on. What I wanted to do is annotate this with the costs. So now we have a little space. If you sum the cost level by level, on the topmost level we do one sink, and we sink down, in this case, the height of the final heap. So the cost of the sink is basically the height. In each step we do two comparisons. We find the larger of the two children and we do the swap, and we have to check if the parent is actually larger than the larger child. On the second level we have 2 times a sink operation, but on a one smaller heap, so one less tall. If you go one level further down, we have 4 times this, but h minus 2. So we go all the way down, and on the last level we have roughly n half, and there's a 0 left. At the very last level we really do nothing. On the levels above we do 1 or 2. And if you sum up these things, you see that the majority of the calls for sink is really at this low level where they are a constant time. So if you sum this up, that adds up to linear in the total thing. So the overall time is linear instead of n log n. I have that written up properly on the next slide. So let's briefly summarize the analysis I did informally. First of all, what is the height of a tree? I think you have an intuitive understanding maybe, but what I really wanted to mean in this module is the number of edges on any root to leaf path, and I want the longest such path. So you can go from the root, any path down, and you count the number of edges you take. The largest number you can get at by walking down to some leaf. That's the height of the tree. Okay? Which also has, it means a node with just a single, tree with a single node has height 0. This one has height 1. This has height 2, and so on. Conversely, we talk about the depth or level of a node as how many edges do I have to go down from the root to reach that element. So this is level 0. That's level 1. That's level 2, and so on. And now you can count how many nodes can I have on a certain level. In particular, if these are full, right, then you have one node on level 0. And for every node on the previous level, you have 2 children on the next level if everything's full. So that means we have on level L, we have 2 to the L nodes if it's full. Right? If you insert 0, then that's 1. If you insert 1, then that's 2 nodes, and so on. So if you sum up the first L levels, and they're all full, that's this sum, which evaluates to the k plus 1 minus 1. Okay? Almost the next power of 2. So the height of a binary heap can be calculated by inverting this formula in a way. We are looking for the smallest k so that the number of nodes I can fit in with k levels is at least n. That's my height, because I need to put the nodes somewhere. I might have some space on the right, remember, but I need to put in at least n. And if you invert that, it means that the height of this heap is log n rounded down. Remember, height is counting the number of edges, so it actually has height plus 1 levels. Right? You start counting at 0 with the levels. All right, that's terminology. I'm just going over this slowly because we'll use that for other bits. And with that prepared, we can finish the analysis of all the operations. Insert was basically dominated by swimming up. We put the new element in the only spot it can go, and then it swims up. And every step brings the new element 1 level up, or some other element 1 level up. Yeah, here actually has to be the new one. And so after at most h steps, h the height of the heap, we necessarily stop. For deleting, the maximum is the opposite. We sink down. Again, we have h steps of sinking at most, but the number of comparisons here is twice that, because we need to compare the children and we need to compare the parent and the child to see if we're done. And finally, the construction. I've already shown you informally how this summarizes. That's the same sum written up properly. You can write this formally as this sum. And the rest is basically something that you would learn in some discrete math class. So I'll basically skip that here, or pretend that you know it. It's tricks like summing in reverse, pulling common factors out, and then looking up sums like this on some formula sheet. Wolfram alpha is something that's useful for that as well. Last slide is summary of all the operations. If you work out what they work in terms of n, these are the running times for all the operations in binary heaps. All right, see you on Wednesday.